Okay, so I'm going to define a few other things before we move on. And the first thing I want to define is what is called radiant energy. So radiant energy is a field. So we'll talk about photometry and radiometry on Thursday, but just know that this is used in many places, in many fields, like radiometry, solar studies, heating, lighting, transmission of information. It is also used in telecommunications. It's also used in fiber optics, all kinds of stuff. So now that I've explained electromagnetic spectrum, let's look at what light is, or what electromagnetic waves are. So remember we were talking about two different ways of looking at particles? One was the wave picture, and the other one is the particle picture. So wave picture says electromagnetic radiation is an electromagnetic wave that carries energy in oscillating electric and magnetic fields. It looks something like this. So I'm going to use red for my electric fields. I'm going to use my green for my magnetic field. So when I look at the wave picture of light, it carries energy within oscillating electric and magnetic fields as the wave propagates forward. When I look at the particle picture, or the matter picture, I say electromagnetic radiation is made up of a stream of particles called photons, and the radiant energy can be viewed as the energy carried by these photons, mathematically given as HF, or HC over lambda. Okay, here's the weird part. So in the photon picture, or in the particle picture, I said the energy is carried by each photon, and that energy is proportional to the wavelength, correct? Very simple. Weird, but simple. What about the wave picture? I never said anything more than just that it's carried in the oscillating electric and magnetic field, right? That's all I said. Now I'm going to tell you something strange. I'm going to say in the wave picture, okay, let me start here. So in the particle picture, I said the energy is carried by each photon, and E is proportional to F. Even though this is a very strange concept, but this is a strange concept that we are familiar with. So it doesn't seem that strange to us right now. But this is going to be a little bit more stranger. So in the wave picture, energy of the monochromatic, do you know what monochromatic is? One color? Good. Wave is proportional to its intensity. So if two electromagnetic waves have the same intensity, but different frequencies, that implies that the wave with higher frequency contains fewer photons, since each photon is more energetic. So I have just given you the combination of the wave picture and the particle picture. So I started off by saying, in my wave picture here, it contains fewer photons. So I've just given you wave-particle duality without actually telling you that that's what it was.